recording is on. All right. Last topic of the chapter on solutions and colloids is colligative properties. This topic deals with a question. Here I have a pure solvent. Suppose I just have a cup full of water. It has a specific boiling point, it has a melting point, it has an osmotic pressure, and it has a vapor pressure associated with it, with pure water. Now suppose I mix something in with the water, sugar, glucose, salt, whatever. How does these four physical properties of the liquid change? How does the boiling point change? How does the melting point change? How does the osmotic pressure change? And how does the vapor pressure change? That's what we're going to discuss today. So the changes in these things is given by these four equations. First of all, just qualitatively, just rule of thumb, the boiling point always goes up on dissolving some sort of impurity, some sort of solute. The melting point always goes down. The osmotic pressure always goes up. And the vapor pressure can either go up or down. Okay? Vapor pressure can go up and down. There's two parts to vapor pressure. If you're forming a solution with a solid solute, so you have a liquid and you're adding some solid, you're dissolving some solid in it, then for sure the vapor pressure goes down. Water has some vapor pressure, put in some salt, the vapor pressure of the whole solution just went down. That's the only case, well, that's one case in which the vapor pressure goes down. Then you can talk about having a liquid solute, right? So for example, vinegar. Vinegar is acetic acid, which is a liquid, dissolved in water, which is also a liquid. So it's a liquid in liquid solution. If you have a liquid solute, one of two things can happen. The vapor pressure can either go up or it can go down, depending on how volatile the solute is. The vapor pressure goes up if the solute is more volatile than the solvent. And it goes down if the solute is less volatile. Okay. I think, if I'm not wrong, acetic acid. Let's deal with glycerin. Glycerin dissolved in water. Glycerin is very gooey. It's very thick, right? If I dissolve glycerin in water, the vapor pressure of the whole system goes down because glycerin is less volatile than water, where in this case. Volatile means how easy it is to evaporate. Does it make intuitive sense that if a liquid is thinner, then it's easier for me to evaporate it versus, for example, acetone. Acetone is very thin. Nail polish remover? For those of you who put on nail polish and remove it, you see how quickly acetone dries off because it's super volatile. It's very thin. It evaporates really quickly. So if I mixed in acetone with water, the vapor pressure of the whole solution will be higher than the initial vapor pressure of just the water, because I have introduced something that's even more volatile. See, that's the argument. Glycerin, on the other hand, very gooey, takes a long time to dry off. If you mix that with water, the vapor pressure of the whole thing goes down, because you have now introduced something that's less volatile than water. Okay, so that's the qualitative analysis part. Now let's put numbers to these properties. So the first thing is that the boiling point goes up. Question is, how far does it go up? So the amount that the boiling point goes up by, the change in boiling point, is given by this equation. I times this constant Kb times molality, little m. Can someone remind me of the definition of molality? Say that. Moles per kilograms of solvent. Yeah. Moles of solute divided by kilograms of solvent. Great. Freezing point goes down. How much does it go down by? That's delta TF. And since it goes down, we introduce a negative sign to compensate for that. This is given by times I times Kf times little m. The osmotic pressure doesn't change, it only increases. In fact, the original osmotic pressure of any liquid is 0. Does that make sense? If you don't put in some kind of solute into your solvent, then the osmotic pressure is 0. Because remember, what was the whole purpose of osmotic pressure? You have these two chambers. Suppose this is salt water, and this is regular water. Things like to flow from higher concentration to lower concentration, so water will naturally flow this way. But to stop that osmotic osmosis, you want to apply some pressure here to make that stop, right? That was the whole purpose of osmotic pressure. The saltier the water here, i.e. the higher the concentration, the more water will want to flow that way. And so the greater pressure you'll need to stop the process from happening. Now suppose I took out the salt water and I made both of these water. Will water flow either way? It's the same, right? So water will not flow either way, so there is no need of any kind of countering pressure. So the osmotic pressure of a pure solvent is 0. Got it? Okay. So the osmotic pressure, it's given by this funny symbol pi for I don't know what reason, but it's given by this equation. I times MRT. I always want to write this in a particular way. You might have seen CRT in class or MRT in class. I like to write it like this. RT times M, and I'll tell you why I'm doing that in a second. Vapor pressure can go up or down. Vapor pressure is, so vapor pressure of what? Vapor pressure of the solution, right? This is the change in boiling point for the solution, changing freezing point for the solution, osmotic pressure of the solution. Here I'm going to put a little SOL because we also have to factor in other pressures. So the vapor pressure of the solution equals I times let's say P naught of A times mole fraction of A plus RK here, I times B naught B times mole fraction of B. What this is saying is, before combining the two components of your solution, right? Suppose this is the solvent, or you know what? Let's not distinguish between solvent and solute. Let's just call this A. Let's call this B. Suppose A initially, just pure A, has a native vapor pressure P naught A, and the component B natively has a pressure P naught B. And then when you combine these in some ratio, the whole solution has vapor pressure P solid, P solution. Okay? And the specific ratio in which you combine A and B is reflected in their mole fractions, chi A and chi B. That's the breakdown of the equation. Great. Very quickly, if component A, if some component is solid, what is its original vapor pressure?
0.
0, right? Because solids don't evaporate. So, for solids, P naught is 0. So if we're dealing with a solid in liquid solution, then the vapor pressure of the solution, suppose A is your liquid, B is your solid. Then this is going to exist as a term, but the second term is going to vanish. It's not going to be there because P naught B is 0 because it's a solid, right? So this is the general form of the equation. Both terms exist if both components of your solution, A and B, are liquid. Example, acetic acid and water, or alcohol and water. But if you're dealing with something like salt water, salt doesn't have any vapor pressure, so it just looks like this. And this will be for water. Got it? Any questions? Yes?
So do all solids have 0 vapor pressure?
Yeah.
Because like dry ice,
Ooh.
straight to
Yes.
gas to
Mm-hmm. So vapor pressure is defined as, I don't think there's a concept of vapor pressure for dry ice because vapor pressure in its definition requires liquid and gas equilibrium, right? That's solid and gas equilibrium, that's a different story. Yeah. So substances that sublimate, they're weird, let's
They don't
deal with them separately, yeah. But yeah, for the purposes of this chapter, all solids have 0 vapor pressure. Great. All right, let's deal with some questions. Before I do that, the reason why I wrote it like this is notice, because there's a bunch of formulas to remember, notice the common pattern in the equations. They all start with I. Oh, I have to discuss what I is in a second. So they all start with I. The freezing thing has negative in front of it because it's the only thing that you know for sure goes down. Then they're followed by constants, right? I times a constant. For boiling point, it's Kb. For freezing point questions, it's Kf. For vapor pressure, it's original vapor pressure of the pure component. This thing has 2 copies of it, right? I times constant, I times constant. And for osmotic pressure, R is the ideal gas constant, and you should think of temperature as also a constant if you're carrying out the reaction at the same temperature. Right? So your R and T are constants here. Just think about it like that. So it's I times a constant times a measure of concentration. For boiling point, melting point, the concentration measure of your choice is molality. For osmotic pressure, it's molarity. And for vapor pressure, it's mole fraction. Right? So the general form is I times constant times concentration. That's how I like to remember these 4 equations. Should make matters a little bit easier to remember. Great. Let's do some questions now. Everyone done writing this down? Yep. Okay. Look at what I did. I stole it from a different class. I guess that's the tradition now. We all steal from each other. whoever took the eraser with them, that's low. That's very low. Like, come on. It makes your life easier if you steal it because now it's with you forever and you don't have to go around finding an eraser. You have to be considerate of others. Alright, here's a question. All four of these formulas are basically the same. You'll basically have the same questions from all four of those formulae. Let's just pick one at random and discuss a question. So here's an interesting one. Suppose, water boils at 100 degrees Celsius. Let's see what happens if I add in a bunch of salt. What does it boil at now? Because that's an important question, right, for those of you who cook. So how high does salty water boil at? So suppose $50 grams of salt is added to, how many grams do you think? 1,000 grams of water. Suppose 50 grams of salt is added to 1,000 grams of water. Calculate the boiling point of the resulting solution. B, the melting point of the solution. I'm adding melting point because answering part B will explain to you once and for all why we add salt to the snow to make it melt. Alright, let's deal with the first one. We'll need some background for this. The boiling point of water is 100. The melting point of water is 0. NaCl has a molar mass of, I don't know, we can calculate it, but I can also look it up. Yeah? 58.5. 58.5 total? Okay. Thank you. Grams per mole. Awesome. So since this is a boiling point question, I'm going to use the boiling point formula. Delta TB equals I KB times M. Oh yeah, KB and KF are constants. Okay, a couple things before we get started with this question. KB and KF only depend on the solvent. Okay? So if you consider two different solutions, salt water and sugar water, the KB and the KF that you're looking at is for the salt, sugar, or the water? Water, right? As long as your solvent doesn't change, your KB and KF don't change, irrespective of the solvent. So KB and KF only depend on the solvent. When you're doing ALEX questions, KB and KF usually is not given to you, but there's a whole table within ALEX where you can go and figure this out. But when you go into that table and look it up, you are trying to match the solvent to the KB and KF, not the solvent. That's the first little fact. The second thing is, what's this funny I? It's called the Van Hoff factor. I think it's silly that chemists came up with a name for this thing, because it literally is, how many pieces does something break down into on dissolution? What does NaCl break down into when you dissolve it? Hmm?
Two.
Two things, but what does it break down into?
And
Na plus Cl minus. So if you just count how many pieces it broke down into, that's 2. So your I is 2. What would I be for magnesium chloride, MgCl2? Yes, so those are the pieces, Mg2 plus 2 Cl minus. How many pieces is that in total? 3 pieces, exactly. What about glucose? What's the I value for glucose? 1, right? Reason? It's molecular. Molecular compounds do not break down. Only ionic compounds break down in solution. So, as a general rule, for all molecular compounds, I is 1. Glucose just remains glucose. Great. Sometimes, so NaCl breaks down into 2 pieces, and so I equals 2 relies on the assumption that NaCl, so if I take 100 NaCl molecules, all of them will break down into 2 pieces. Right? NaCl fully dissociates in solution. All of it breaks down in solution. And then there's the other extreme where none of it breaks down in solution, glucose. But there's also intermediate ones, partially soluble ion compounds. For example, if you take silver chloride, it's only partially soluble in water. Like if you take 100 molecules of AgCl, maybe 25 will break down, but 75 will remain intact. So would I be 1 or 2 for that kind of compound? Sure. Turns out we take averages. So I there will be a decimal number. It will be like 1.3, 1.5, 1.7, whatever it is. Right? It doesn't mean that a molecule breaks down into 1.7 pieces. It just means on average it breaks down into 1.7 pieces. Okay? Usually, if you're not given I, it's either one of 2 cases. It's molecular, so you know I is 1, or it's ionic. You can write down the pieces that it breaks up into and calculate the I value. If you'll never be asked a question where you're supposed to know the I value, but I is not a whole number, like I equals 1.3. If you are dealt with such a question, the whole question will be to calculate I. Everything else will be given to you. Okay? Maybe we can do a question like that, but let's do this one quick. All right. Oh yes, let me give you the Kb and Kf values for water. This is what you need to memorize actually. I bet you have seen this in class. 0.0521. That is Kb and Kf is 1.86. So memorize these 2. Or not. Maybe the professor will give it to you on the test. When I had Chem 2, he didn't. Well, not this professor, another professor didn't. So we had to memorize that. It's only 2 numbers. Okay. All right, now let's start plugging in different things. I keep forgetting there's more and more stuff to add as an aside. Notice all of the boiling point and the freezing point questions have a delta in them. Delta usually means change, final minus initial. Here there is no final initial. Here delta means, well, it is sort of like final minus initial. Here delta means solution minus pure. Okay? Solution minus pure. So delta TB is boiling point of solution minus boiling point of the pure solvent. Same thing with delta TF. And for the solution, we just write it as T. So TB or TF. For the pure part, we put this little extra 0 on top, T naught. That's conventional. So TB would be boiling point of the solution, T naught B is the boiling point of the pure solvent, TF, and TF is 0. Solution versus pure. All right. just to familiarize ourselves with some notation. Awesome. Let's expand this real quick. TB of the solution minus TB of the pure solvent equals I times KB times M. All right, what's my TB? Or what do I know that I can plug into this equation?
100.
Where does it go?
T naught.
T naught, right? Good. 100 for T naught. Great. So that's 100. By the way, in these questions, delta T of delta TB, it doesn't matter if your temperature is in Celsius or Kelvin. It'll give you the same answer. But for the osmotic pressure question, your T must be in Kelvin. Okay? The reason why is because if your formula involves a change of temperature, then you're free to use either Celsius or Kelvin. Both work. But if your formula involves T, not delta T, just T, you must use Kelvin. Yes?
Oh, I just couldn't hear the first part because I got it.
The first part,
So basically, you said for osmotic pressure it has to be in Kelvin, but if there's a change, then it doesn't matter.
for osmotic pressure, your T must be input in Kelvin. For Celsius, for delta TB and delta TF, so boiling point, melting point questions, doesn't matter. Celsius or Kelvin, but don't use Fahrenheit. That's just, we're not going to use that in science. Okay, cool. TB is unknown because that is the question. Calculate the boiling point of the solution. What's the I value for NaCl? 2, good. Kb for water, 0.52. And lastly, we need to calculate the molality of the solution. It's going to be moles of solute divided by kilograms of solvent. Which one do I know immediately?
Kilograms of solvent.
How much is that? 1 kilogram, right? 1,000 grams is 1 kilogram. Great. The top, I need to calculate the number of moles. I know I have 50 grams. I'm going to divide that by the molar mass, which is 58.5 grams per mole. Can someone tell me what this is? Yeah. 0.85. Thank you. Awesome. 0.85 goes here. Just put some parentheses to make that clear. All right. Only one variable remains in the equation to be solved for, which means we can go ahead and solve it. TB is going to be 100 plus this mess, whatever that is. What is that? Yes. 0.89. So it's 100.89 degrees Celsius. Higher than 100 degrees Celsius, not that much higher. Right? So the effect is there. You might gain a second or two or maybe a minute by the time your pasta is done. Not that much. So it's fine. You can go either way. But it tastes better if you salt your water. Now that's important. Great. Let's very quickly do the melting point part. Why don't you take 5 and do the melting point on your own? Yes?
Just a quick question, but then how factor doesn't have a unit?
No, unitless. All right, do part B on your own. Take 5. right? Someone have a final answer? Anyone have a final? Yeah.
Negative 3.16 degrees
Negative.
Celsius.
That's your delta TF.
That's
Yeah.
my final, not my delta.
Yeah. So it goes down by that much. But then if I just want the final freezing point, you would do 100 minus that. Say that again.
Like, is it gonna be positive? No.
Your delta TF will be negative.
No, the TF.
TF will be positive. Yeah. Yeah. Well, actually, oh, I see what you're saying.
Because it's 0 degrees, so it's.
Correct. Yes. I messed up. Great. Delta TF minus T naught F is minus IKFM. This is unknown. This is 0 to 1.86. M is the same as the one we calculated. 0.85. Yeah. What is it? Negative?
Negative 3.16.
3.16 degrees Celsius. That's why you solve snow. Yes. Say that again.
How come you put a negative in front of the formula?
For the formula? Oh, that's the formula. Yeah, the formula has an I. Yeah. So what this means is you need to lower the temperature all the way to negative 3.16 degrees before water turns into ice. Right? Now, usually it's 0, right? You hit 0, you make ice, you make snow. But suppose the temperature is negative 2 degrees Celsius. It's below freezing for normal water, so normal water will start to freeze up. But then you salt the water, which will drop the freezing point to negative 3.16. You need to go all the way down here to start freezing water. So this is above freezing for the salted snow. So it will remain liquid.
So it's 50 grams. This 3.16 degree for 50 grams. So if we add more salt, then it's going to be more.
Exactly. Yeah. This is a good estimate this is realistic values for cooking, right? We don't, yeah. Like pasta water, this is a good amount. This is like a handful of salt. Yeah, 50 grams. But, when you salt your snow, you do it like crazy. It's probably more salt than water or something. So this drops tremendously. So even though it's frigid outside, well below freezing, for water, for the salty water, it's not freezing yet. So it will remain liquid, which is why the snow melts. Great.
I have a question.
Yes.
So the I value over there is 2 for NaCl,
Yeah.
and then 0.52 is the kb for water, right?
0.52 is the kb for water. Yeah.
Okay. So we use the I value of the.
Yeah. Yeah. So the I value is always for the solute, except in the last equation where you have the vapor pressure equation. I gave you two I values, IA and IB. That's because if you have two different components, one may break down in solution, the other one might not. So it's to distinguish the two. Yeah. Okay. Awesome. Another question that comes up in this section is as follows. Biologists are interested in this sort of question. It's a very natural question. Suppose a biologist working in a lab was able to isolate some sort of mystery protein. No one knows what this protein looks like. No one knows how massive it is, or what the structure is, and so on and so forth. You're trying to figure it out. You're trying to play a detective game. Now, there exists no microscope that can look at molecules and see where all the atoms are. Molecules are way too tiny for microscopes. So you need an indirect method to determine these features of the molecule. its mass, its structure, and so on. One of the easier things to do is to figure out its mass using this colligative property stuff. And that is by measuring, so dissolve a known amount, take your mystery protein sample, maybe measure 2 grams of it, dissolve it in water, and then measure the osmotic pressure of the resulting solution. That will tell you the molar mass of your protein, right? So you can measure grams, that's easy. All you need is a scale. You can measure osmotic pressures, it's also easy, don't need much sophisticated equipment. Using these 2 very basic measurements, you can figure out the mass, the molar mass of the molecule, which is great. So let's do a question that deals with that. 2 grams of a mystery protein is dissolved in 100 grams of water, and the resulting solution was found to have an osmotic pressure of 0.1 atm. ATM is a unit of pressure, atmospheres. Determine the molar mass of the mystery protein X. Molar mass, yeah. Molar mass of the mystery protein X. Okay. What equation are we going to use? We only have 4 equations, right? What do we use here? Yeah. The yes. Well, it's osmotic pressure question. We use the osmotic pressure formula. I equals I RT minus molarity. Great. Let's start plugging in the information that we know. What do we know? What's 0.1? Which is pi. I, it's a protein. Proteins are molecular. So that's 1. R, another thing that you need to remember, ideal gas constant. In this chapter, solutions and colloids, the R value that there's multiple R values, but in this chapter you're going to use this one. The other value is, and the easy way to distinguish between the two is if you have liters involved anywhere or pressures involved anywhere, that's what you default, 0.0821. On the other hand, if you have energies involved, joules, you're going to use the 8.314 one. Yes. Say that again? No. The unit is something else. I can figure it out, but it's something. I'm just giving you a pointer on which value to use depending on the context. If you see liters, When you see liters, molarity involves liters, right? So you're going to use the 0.0821. But in later chapters, example thermodynamics, that whole chapter deals with energies. So you'll always use 8.314. So that's the little thing. Okay, 0.0821. Oh, I didn't give you the temperature. 25 degrees Celsius, room temperature. What is that in Kelvin? Yeah.
And what was the second one?
Say that again.
The second one.
8.314 with energies. Joules.
No. I mean after liter.
Oh, liters or atmospheres. If you see any of those two units in your question, you know that's the value you're using. All right, so 25 degrees Celsius, what is that in Kelvin? 298.15. Yes. How do you get that?
273.115 plus.
Exactly. You take your degree Celsius temperature, you add 273.15. That gives you 298.15 times molarity. We don't have molarity, so let's try and plug in the pieces of molarity that we do have. What goes on the bottom? Liters of water, liters of solution. I have 100 grams of water. What's the volume of 100 grams of water? 100 milliliters. Remember, density of water is 1 gram per milliliter. So grams you can directly convert into milliliters. It's the same ratio. Yeah?
Can you repeat that?
The density of water is 1 gram per milliliter. So if you have X grams of water, it's X milliliters of water. Since we have 100 grams, that's 100 milliliters of water. We're going to approximate the volume of the solution to remain unchanged. So it's also 100 milliliters. So what goes on the bottom? 0.1. You want to convert that into liters. 0.1 liters. Great. So up top goes number of moles of the protein. We don't have number of moles in the question, so let's expand number of moles. What goes on top? How do we calculate number of moles?
Mass of the solid.
Mass of the solute, which is given, 2 grams. And what goes on the bottom? Molar mass. I have no idea what that is. But good news for us, that's the only unknown in the entire equation, which means we can solve for it. Yeah? That's it. Solve for mm. Someone do this for me. Let me know as soon as someone has a value. $4,895.
4,895.
0.6
approximately that much. Big, huge molar mass. It makes sense because proteins are very, very big. This is a usual mass for protein. They could go into the 10,000s, they can go into 100,000s. They're huge molecules. Any questions on how this was done? No? Yeah.
I got a different answer because I used 0.08206 to get it around the.
Yeah, that will give you a slightly different, but it should be like in the thousands.
Okay.
Did you
So
get it?
always round the R or?
It's fine. However, yeah. Ask the professor what his favorite accurate value of R is. I don't know. It's something. It's a number. Yeah. Great. Proteins are big. Remember, we use VSEPR theory to figure out the shape of small molecules, right? We count the bond pairs, we count the lone pairs, and then we get like, this is Chem 103 stuff. Tetrahedral, or, what is it? Square bipyramidal, all that stuff. All of those rules only apply to small molecules. When you get huge molecules like this, figuring out the shape actually becomes a very hard problem. People spend sometimes an entire PhD just trying to figure out the shape of one protein. And that's their PhD. They have to come up with several inventions, several mathematical methods to do various calculations, and that's how they find the shape of a protein, right? If you, on your own time, Google the structure of any protein that you know, or just structure of proteins, you'll see it's a huge mess. It's like a crumpled bunch of, there's no way to make sense of the structure. It's all crumpled up, it's all weird. But the interesting thing is, all of those proteins look exactly the same. They're the exact same crumpled mess, right? So that's why we try and figure out the structure. And also, proteins function primarily based on what their structure looks like. So if you want to know how a drug is going to, interact in your body, you better know what the structure of proteins are, because structure tells you function, right? That's the necessity of figuring out the structure of these big molecules, proteins. Awesome. We have about 20 more. Let's get started on the next chapter. This is it. This is solutions. Just to recap, what did we do? We figured out 3 different ways to measure the concentration of a solution: molality, molarity, and mole fraction, right? Then we talked about solubility. Things can only be dissolved up to a maximum limit. That maximum limit is what we call solubility. It's the maximum amount of solvent that can be dissolved in a given amount of, maximum amount of solute that can be dissolved in a given amount of solvent. After that, we formed our solutions, and then we studied 4 of their properties: boiling point, melting point, osmotic pressure, and partial pressure. Another name for vapor pressure. Okay? Great. This is it. Next chapter, chemical kinetics, deals with the question, how fast do reactions take place? What does the speed of a reaction depend on, and how do we measure the speed of a reaction? What does it mean? How do we put a number to that description? Here's an example equation. If you mix nitrogen gas with hydrogen gas, they combine in this ratio to form ammonia, NH3. Ammonia, very important. Smells terrible, but very important. NH3. This reaction can either take place fast, slow, right? It has a certain rate at which it's happening. That rate can be related, so the rate of the reaction can be related to the rate of consumptions and productions of the various species in a chemical reaction. Right? So the reaction has a certain speed. Due to that speed, these reactants are getting consumed at a certain rate and the products are getting produced at a certain rate. They're not all the same. Right? That's the crucial thing to remember. Not all species, so species means reactants or products, in your chemical reaction get consumed or produced at the same rate. Why? Because they're not being used up in the same ratio and not being produced in the same ratio. For every molecule of N2 that gets produced, that gets consumed, 3 molecules of hydrogen get consumed. So which one's getting consumed faster? So if I in a second, if 5 molecules of nitrogen get consumed, 5 times 3, 15 molecules of hydrogen get consumed. Which one's getting consumed faster? Hydrogen is getting consumed faster. And only 2 times 5, 10 molecules of ammonia get produced in that second. Right? So you see how they're not all getting consumed at the same rate or produced at the same rate? There are differences. But the relation between each of them is always fixed. If you know how fast this is getting consumed, you can immediately tell me how fast this is getting consumed and how fast this is getting produced. They're all changing, they're all getting consumed or produced at some rate, but all of those rates are related to each other very rigidly by the stoichiometry of the equation, by the coefficients in the equation. Yeah? So our first goal is to relate the rate of the reaction to the rates of consumptions and productions of each species in the reaction. The way we do that is, has anyone taken calculus here, Calc 1? You don't need any calculus, but it helps. Remember this thing, rate of change in calculus, ddt, dy dx, derivative, right? Oh, first of all, our favorite concentration measure in this question will be molarity. Remember last question we used molarity, molality, and mole fraction. This chapter we're only going to stick to molarity or pressure if it's gaseous reaction. And molarity is going to be denoted by these square brackets. Instead of big M, we're going to use square brackets. That's molarity. Okay, we have 3 species, nitrogen, hydrogen, and ammonia. Rate of consumption of nitrogen is given by ddt of the molarity of N2. How fast the molarity of N2 is changing with respect to time. That's what this means. Okay. This is the rate of consumption of nitrogen. What about hydrogen? What would that be? Same thing, same format. It's just the molarity of hydrogen, just rate of consumption of hydrogen. Rate of consumption or production of ammonia is dNH3 divided by dt. Make sense? You're not going to treat this as a fraction. This is one object. Okay? That's one object. Either you're given the value of this object or you're asked to calculate the value of this object. You're not being asked the value of this or this separately. It's always, think of that as one thing. Alright? Okay, so the rate of the reaction, the way all of these are related to each other and to the rate of the reaction is as follows. If you're considering a reactant, put a negative. If you're considering a product, put a positive. Right? Negative, positive. Negative for reactants, positive for products. And divide out the coefficients. So, rate of the reaction will be equal to nitrogen, reactant or product? Reactants are negative. Any coefficients out front? None. So that's just it. Rate of change of nitrogen with respect to time. Hydrogen, positive or negative?
Negative.
Negative because it's a reactant. Coefficient 3, so I'm going to divide that out. 1 over 3 ddt of hydrogen. Ammonia, positive or negative?
Positive.
Positive. And any fraction?
Yes, half.
1/2. Divide out the coefficient, which is 2, so that gives you 1/2 ddt of ammonia. Make sense? This is how all the rates are related to each other. This is not one equation, it's a series of several equations. This equals this equals that, this equals that equals this, all possible combinations. Alright? Now let's do a question from this section. Suppose in the above reaction, the reaction above, hydrogen is consumed at a rate of 20 molars per second. Calculate a rate of consumption of nitrogen, rate of production of ammonia, and C, rate of reaction as a whole. Okay? Calculate A, rate of consumption of nitrogen, B, rate of production of ammonia, NH3, and C, rate of the reaction. Great. This is going to be very easy. What's given to us? The rate of consumption of hydrogen is given to us. What's the, how do we write that? Yeah, it's ddt of hydrogen. This is given to be 20. That's what we're given. Yeah? The whole object's value is given. It's 20. But you have to be careful. Rate of consumption means the thing is getting consumed, which means its concentration is going down with time. So you have to introduce a negative. Consumption is negative. Production is positive. So when you read the question, the value gives you the value, but then you have to read the word for the positive or negative. Consumption means negative. Awesome. Part A, we need to figure out ddt of N2. This is being asked. So far, so good? So we just need to relate these two. let's go and find where these two are located. There's my DDT of hydrogen, there's my DDT of nitrogen. So this is, we're gonna maintain tunnel vision and only look at this part of the equation. Let's copy that. Negative DDT of N2 is negative 1/3 DDT of hydrogen. Yeah? Now let's just plug in our values. This is unknown. Negative 1/3. What is this? Negative 20. The negatives cancel. 20 divided by 3. And so DDT of N2 is 20/3 molars per second. Oh, it's there's a negative, right? Yeah. There's an overall negative there.
So,
Yeah.
so you mean, negative cancel each other. So you need to add like the negative sign because it's.
No. This is all automatic. There was a negative sign there. See, negative, negative, but the value itself is negative. There's 3 negatives. This negative here is just a result of algebra. Yes.
Why wouldn't you divide by -1 then to get rid of the negative for N2?
Sure. Divide both sides by a -1. That will get rid of this negative and one of these. Let's say that one. But there's still another negative remaining.
Well, when you multiply both of them first, wouldn't they cancel out? And
Sure. Then this will become positive.
Oh, okay.
It doesn't matter which way you do it. Yeah.
Got it.
So that's negative 20/3 molars per second. Okay? Alright. Let's do the next one. Exactly the same method. We just need to go equation, yes.
So you put the negative in the 20, right?
Yeah.
Because it gets consumed, but we also did that in the relationship thing. We make reactants negative because they get consumed, right?
Yes.
So how come we dump there's negatives in both?
These negatives are just to relate the rates to each other, but then depending on whether they're themselves getting consumed or produced, we need to introduce an additional negative.
Oh, okay.
Yeah.
Okay. So depending on what they tell us.
Yes. Exactly. All right. Part B: rate of production of NH3. We want this guy. We have, well, now we have both of these guys, right? We have DDT of N2 and DDT of hydrogen. Let's just go with the hydrogen. So there's hydrogen and there's ammonia. Yes.
Just referring back to part A, so which would be the positive one if H2 were being produced? Would it be the rate of the reaction for H2 or the number that they give?
This thing will always remain as is.
Right, but if they were to say H2 is produced instead of consumed?
Positive.
Which one is positive? The negative one?
If they say that the rate of production of hydrogen is 20, well then you'll say DDT of H2 is positive 20.
Okay, and
Yeah.
then it would, okay.
Okay. So for part B, we need to relate ammonia and hydrogen. Ammonia and hydrogen. So I'm going to look at these two now. Okay, that's a third DDT of hydrogen, which is positive 1/2 DDT of ammonia. This is what I'm trying to solve for. Hydrogen is negative 20. This big object. You wanna solve for this, so send the 2 over, and that gives you what do you get? What do you get if I solve for this? Send everything else over? 40 over 3. Hold on for a second. Right? Last question. Let's figure out the rate of the reaction. Rate is over here. Hydrogen is over here, so let's compare these two. So that's negative 1/3 times negative 20, which is 20 over 3 molars per second.
Wait. That's the rate of the whole reaction?
That is what we define to be the rate of the reaction. The rate of the reaction doesn't tell you how fast each individual species are changing with respect to each other. It's just like a common denominator for all.
Okay.
Yeah.
So you're just using what's in the relationship to find out.
Exactly. Yes.
So is the rate of reaction always positive too?
Yes. Correct. Rate of reaction, if you use that formula correctly, it will always come out to be positive. That's how it's defined. No deep reason for that. That's how we define it. Okay. All right, we are at time. There was an attendance sheet that was being passed around. If anyone hasn't signed their name, it's out front. All right, I'll see you guys next week.